Here we are going to discuss mass conservation. So one of the important principles that lead to the Navier-Stokes equations, and in particular we'll discuss mass conservation at the control volume level. And the first thing that we are going to do is to derive mass conservation on the control volume. All right, so let's consider that we have we're looking at a particular system where there is flow. I'm going to represent this with these lines here. These are neither streamlines nor path lines. This is just a way of representing flow. And let's say we want to focus on this particular region of space here. We are interested in this particular region, and so we'll define a control volume. So we're going to draw here a control volume. That is one particular, and in that case completely arbitrary, region of space, which I'm going to call my control volume, which I often just denote CV. So the control volume is made out of all of the everything which is inside of this region of interest and which is surrounded by this control surface here. So it is surrounded by here our control surface, which I will often call just CS. And there are many ways of choosing a control surface, and in this particular derivation I'm going to assume that this control surface does not move. So that means that neither the control surface nor the control volume change with time. So they're completely, they do not change with time. And so the first thing I want to do is to find a statement of mass conservation for this control volume. So here is how you can construct such a statement of mass conservation. We can consider, it makes sense to consider the total mass inside of the control volume. And as I said before, in physics or in mechanics, oftentimes you're not so much interested in the quantity, but you're actually much more interested in how it changes. So the interesting quantity might not be exactly how much mass there is in this control volume, but here we're more interested in how it changes. So let's start with looking at the rate of change of total mass inside the control volume. And when I say rate of change here, I mean rate of change with respect to time. Okay, so let's look at this quantity. How does the total mass inside of the control volume changes with time when mass is conserved? So one thing you could say is that, all right, if total mass is conserved, that means that this rate of change is 0. Now that would actually be a wrong statement of mass. If you look at this picture here, you see that there is flow, so there can be a flow coming in or coming out of the control volume. And so depending on how much flow is coming in or coming out of the control volume, the total mass inside of the control volume could change. So this quantity here ought not to be equal to 0. And now if you think of what happens when the rate of change of total mass inside my control volume isn't equal to 0, then you clearly see that if you have mass accumulating, for instance, inside of this control volume, that means that more mass is flowing in than mass is flowing out, for instance. And therefore, the rate of change of total mass inside of the control volume, if mass is conserved, needs to be balanced by the net mass flow rate through the control surface. So when we consider this control volume, we'll say that the rate of change of total mass, that mass is conserved if the rate of change of total mass inside the control volume is equal to the net mass flow rate through the control surface. And by net, I mean a little bit the difference between what comes in and what comes out, so the net mass flow rate. So how can we write this statement here in mathematical terms? So how can we now deduce from there a mathematical statement? So first we need to express mathematically the total mass inside of the control volume. And so how can we write this mathematically? Well, this control volume is made out of an infinite amount of those very tiny small differential element of volume, which I'll call dV. So this is a small dV, a differential element of volume. And what is the mass of this small differential element of volume? It is the density times this small volume. So the mass of my differential element of volume is rho times dV. And now if you want the total mass, we need to add up all of those small elements of dV over the entire control volume. So we need to integrate over the entire, take a volume integral over the entire control volume. Now this here is going to be the total mass. Now we're not looking at just the value of the mass, but we're looking at how it changes with time. Now we're fixing a particular control volume, and so we're looking at the mass inside of this control volume, and the mass inside of this control volume is therefore only a function of time. So we can take the straight derivative of this quantity, and that is going to be our rate of change of total mass inside the control volume. And when I mean rate of change, again, I mean rate of change with time. And that has to be equal to the net mass flow rate through the control surface. So how much mass flows through the control surface per unit time. Note here in terms of dimension, this will have the dimension of a mass per time. And therefore what we want here is really how much mass goes through the control surface per unit time. Well, just like when we looked at the mass inside, if we're looking how much mass goes through the surface, well, we have mass going through the surface at every single piece of the surface. So here we have mass going through this piece of a surface. In my drawing, the mass is actually coming in through this little piece of surface. I also have mass coming out, for instance, of this little piece here of the surface. This little thing, piece of surface, I call ds, and this is a differential element of surface. And at every one of these pieces of surface, we can associate a normal vector, n, which we always assume is pointing outside of the control volume. So n here is a unit vector, so unit normal vector, pointing outside of the control volume. And this unit vector n is defined at any given point on the surface. So here, for this little ds here, my unit vector would be pointing normal outside of the control surface. Alright, so of the control volume, sorry. Okay, so how much mass goes through this small ds per unit time? So remember here we said that if we have an element of volume dV, then the mass of this element of volume is rho dV. Now likewise, if we are thinking about how much mass crossed this little ds per unit time, what we need to do is to find out what volume of material, of air, or of liquid, what is the volume that crossed this surface ds per unit time, and multiply this by the density. And the volume that crossed this surface ds per unit time is the volumetric flow rate. So there is a video on what the volumetric flow rate is, but if you remember from that video, the volumetric flow rate is the volumetric flow rate is u, the velocity vector, dot n ds. This here is the volumetric flow rate through the differential surface ds, which represent how much volume crossed the surface ds per unit time. So this here is the volumetric flow rate through ds, and it represents how much volume went through ds per unit time. So the units are meter cubes per second. So we see here we have meters times meters squared per second. Alright, so this is the volumetric flow rate. The mass flow rate is just going to be this volumetric flow rate times rho. Alright, so this here is now going to be how much mass went through ds per unit time. And if we want to know what was the net mass flow rate through the control surface, then we simply have to integrate that here over all of these ds. So we have to integrate over all of these ds over the entire control surface cs. And now, because this control surface is always a closed surface, it is a closed surface because it bounds a given volume, so it's closed. And we'll always write this integral here with this little circle. And now here we always have to stop and think about our signs, and think about our signs the following way. Let's assume here that the total amount of mass inside of my control volume decreases in time. If we have conservation of mass, if this total amount of mass decreases in time, then you will get that I will have more mass coming out than mass flowing in. Right? So if the mass here decreases in time, that means that my net volumetric flow rate flowing outside of my control surface is positive. Right? So if this number here is negative, so if the mass decreases, then this number here is positive. And that can only be possible if in my formula here I have a minus sign. So this is a statement of mass conservation on our control volume. Can also write it as the rate of change of mass inside of my control volume plus the net volumetric flow rate through CS equals 0.